אחר צהריים טוב לכולכם. בשם הפקולטה למתמטיקה ומדעי הטבע אני שמח לארח את חתן פרס נובל לכימיה דן שכטמן. אני שמח על ההזדמנות שהביקור שלו אצלנו נותן לי, שוב בשם הפקולטה, להוקיר אותו על פועלו העצום, גם פועלו המדעי וגם המשמעות הישראלית מדינית שיש לפועל הזה. אבל יש גם מטרות נוספות בהזמנה ששלחתי לדני לבוא להרצות אצלנו. ראשית, אנחנו מעוניינים להכיר ולשמוע על ההמצאה עצמה, מהם הקוואזי-גבישים, ולהבין מה המשמעות של ההישג הזה מבחינת הייחודיות שהביאה להענקת פרס נובל. אנחנו גם רוצים ללמוד משהו על הנושא של השחייה נגד הזרם שאפיינה את תחילת דרכו, והדרך שהביאה להישג העצום הזה. אז כאמור התחילה בשחייה נגד הזרם, אבל באיזושהי דרך הדבקות הזאת שלו במטרה, ככה אנחנו רואים, הביאה לא רק להפיכת כיוון הזרם, אלא הזרם עצמו הפך לאיזשהו נחשול ענק. ואנחנו רוצים להבין מה היו המניעים האלה, האם זאת הדרך שלנו כמדענים להתמודד עם מחקר, המצאות, חדשנות, או אולי, אני אפילו שאלתי את עצמי אם היה משהו מיסטי שקשור לסימטריה המחומשת שעומדת בבסיס התגלית הזאת, שהיא מאפיינת תרבויות שונות, כמו למשל התרבות היפנית. אז גם על הדברים האלה אולי נשמח לשמוע מילה או שתיים. הנושא הזה של שחייה נגד הזרם הוא לא הפעם הראשונה שאני יודע מההיסטוריה של דני שהיכולות שלו וההישגים שלו לא הוכרו. אני למעשה מכיר אותו, אני לא יודע אם אתה זוכר, מאמצע שנות ה-70, כשאחרי מלחמת יום הכיפורים מתישהו נקראנו לשירות מיוחד באיזו יחידה של חיל האוויר שעוסקת בחומרים, והיה צריך שם מומחיות בחומרים. ויום למחרת ההתייצבות שלנו מצאנו את עצמנו באיזה ארכיון מאובק של היחידה הזאת, והתפקיד שלנו היה לסדר את הארכיון. זו הייתה הפעם האחרונה שנפגשנו במילואים, כי שנינו החלטנו שזה לא הדברים שאנחנו נעשה מבחינה מקצועית, אבל אני חושב שהם בוודאי גאים לדעת שנובליסט סידר את הארכיון שלהם. זה היה אחד מההישגים הלא מוכרים עד אז. לפני שאני אזמין את דני לספר באמת את הדברים האלה, אני מבקש מפרופסור שרה סטרום, זה הרקטור האוניברסיטה, לשאת כמה דברים בשם האוניברסיטה.
תודה לפרופסור גד מרום, דיקן הפקולטה למתמטיקה ולמדעי הטבע, וברכות לאורחנו הנכבד, פרופסור דן שכטמן, ולכל מי שנקבץ לכאן לשמוע את דבריו. עיקר דבריי מכוונים לקדם בברכה את פרופסור שכטמן בשמי ובשם האוניברסיטה העברית. יש כבר מסורת של פרסי נובל בארץ, ופרופסור שכטמן, כפי ששמענו בדרך טיפוסית, לא מורד במסורת, ובניגוד לקודמיו הוא לא בוגר האוניברסיטה העברית. אבל האוניברסיטה העברית, כמו ירושלמיות אחרות בשעה הזאת, לא סובלת שמדירים אותה. ובקיץ הקרוב פרופסור שכטמן יצטרף לחבריו הנובליסטים האחרים עם קבלת תואר דוקטור כבוד של האוניברסיטה. אז תנו לנו זמן. אני כמובן לא אדבר על המחקר של פרופסור שכטמן, ההיכרות שלי עם כימיה נגמרת באלכימיה של ימי הביניים, שזה אגב היה המקום שבו התחילו לעשות ניסויים אמיתיים, אבל זה היה בשביל אלכימיה. אני מודה לפרופסור שכטמן שהסכים להרצות בפנינו על מחקרו. אני מבקשת לומר מילה על המסגרת שבה הוא וגם אנחנו פועלים. ואני חוזרת לראשיתה של המסגרת הזאת. שנת 1925 הייתה שנה טובה לאקדמיה בישראל. ב9 לפברואר התקיים על הכרמל בחיפה טקס הפתיחה לטכניון, עדיין טכניון בתו. פחות מחודשיים אחר כך, ב1 לאפריל, התקיים על הר הצופים טקס הפתיחה של האוניברסיטה העברית בירושלים. ובלי להיכנס לתחרות הידידותית בין שני המוסדות על השאלה מי האוניברסיטה הראשונה בארץ, שני המוסדות האלה בגרו, ובגרותם אינה מביישת את ינקותם. עבור מי שמתבונן מן החוץ, גם השנים האחרונות הן שנים טובות לאקדמיה בישראל. דן שכטמן הוא איש הסגל האקדמי הישראלי, חבר סגל פעיל, החמישי שזכה בפרס נובל תוך פחות מעשור. אבל כמו קודמתו וקודמיו בכתר הזה, גם הוא ראה ורואה את עצמו כשליח ציבורנו, ומיד הדברים הראשונים שהוא אמר היו להתריע מעל כל בימה על מצוקת המחקר והחוקרים בישראל. פריחתן של אוניברסיטאות בעולם, בכל מקום ובכל תקופה שבה הגיעו לפריחה, הייתה מבוססת תמיד על איזון של שני מרכיבים. תמיכה מסיבית של גוף מממן, שיכול להיות הכנסייה או האצולה או המדינה, מצד אחד, ושמירה על מידה רבה של עצמאות מצד שני. בכל מקום שבו הופר האיזון החל תהליך של הידרדרות. במדינת ישראל נחלש בעשור האחרון המרכיב הראשון, שזה תמיכת המדינה, ולצד הרחבת מערך המכללות, התמיכה הציבורית באוניברסיטאות המחקר קוצצה באופן שיטתי ונמשך. ואותותיו של קיצוץ זה ניכרות בכל פינה באוניברסיטאות. בשנתיים האחרונות אנחנו שומעים אמנם צלילים אחרים, יותר הבנה למקומה של השכלה גבוהה, ברמה גבוהה, ולמקום המחקר המדעי בעתידה של מדינת ישראל, והבטחות, בינתיים רק הבטחות לתמיכה גדולה יותר. ההבטחות טרם מומשו. צריך להוסיף שזעקתם של תחומים כמו טכנולוגיה, מחשבים, ביו-רפואה, מתקבלת לפחות עקרונית בהבנה, אבל עדיין נעדרת מהשיח ההתייחסות הרצינית אל הצורך בהבנה מעמיקה ובמחקר מעמיק במקצועות האלה, וגם במקצועות כמו כימיה, התשתיות משוועות לשדרוג. במקביל, הולכת ומתגברת הדרישה, הלכה למעשה, למעורבות יותר גדולה של המדינה בניהול האוניברסיטאות, וליותר מה שקוראים רלוונטיות, קרי תכליתיות של הנעשה בהן. ועל כן יש להזכיר, התנאי השני לפריחתן של אוניברסיטאות, עצמאות אקדמית, אינו עניין ניהולי גרידא. הוא קשור קשר הדוק ליכולת של הסגל האקדמי, הפועל מתוך קשב להתקדמות המדע, ליזום מהלכים אקדמיים, לתכנן ולפתח את התכנים האקדמיים, ליזום מחקר חדש. מעורבות כזאת היא נשמת אפה של היצירה המדעית התרבותית. בלעדיה יהפכו האוניברסיטאות למשרדים ולמפעלים, בעלי תוצר ותפוקה, ועם הזמן פחות ופחות בעלי שאר רוח. ההשפעה של שינוי כזה תתבטא במוקדם ולא במאוחר בהורדת רמת החינוך האקדמי, בפגיעה ביצירתיות ובניוון של המדע, המחקר והתרבות בישראל. וחשוב להבהיר כי חזות קשה זו אינה ניתנת להוכחה כמותית ומדידה, אבל היא מבוססת על ניסיון היסטורי. האוניברסיטאות הראשונות בהיסטוריה צמחו ככל הנראה בעולם הערבי. אוניברסיטת קראוויין בתוניס שנוסדה בסוף המאה התשיעית, אוניברסיטת אל-אזהר שנוסדה בקהיר במאה העשירית. האוניברסיטאות האלה קבעו את סדר היום האינטלקטואלי של זמנן, ועל רקע זה מתבקש הסבר להבדל העצום בין מקומה של אוניברסיטת אל-אזהר היום למקומה אז. אחד ההסברים, לא בהכרח הנכון, אבל אחד ההסברים הרווחים מתמקד בשאלת הרלוונטיות. לפי הסבר זה, כאשר שלטונות המדינה ושלטונות הדת הגבילו את הכרתם ותמיכתם למקצועות הרלוונטיים, קרי השימושיים, כמו אסטרונומיה שמאפשרת חישובי זמן תפילה, מתמטיקה שמאפשרת חישוב כיוון התפילה, מכניקה שמועילה להנדסת מים, באותו רגע נגזר דינו של המדע והיצר המדעי לשקוע. מתארח אצלנו אדם שכפי שנאמר כבר בעשרות כתבות הוכיח את כוחו של השכנוע המדעי הפנימי וההתמדה במתודולוגיה שעיקרה הוא חיפוש האמת. הוא והצלחתו הם גם הוכחה חדה מאין כמותה לחשיבות העצומה של חופש מדעי, של ביטחון כלכלי לאנשי מדע, של אורך רוח ומתן מרחב פעולה לחוקר שאינו נדרש לספק רלוונטיות מיידית. וחוץ מזה שהוא הוכיח את זה, הוא כנראה גם הוכיח את קיומם של גבישים קוואזי סדרתיים, ועל כך אני מקווה שיספר לנו היום. תודה.
לא נותר לנו אם כך, אלא להזמין את פרופסור דן שכטמן לספר לנו על תגליתו.
צהריים טובים לכולכם. שומעים. אחרי הדברים החכמים האלה מפי הדיקן והרקטור, ניקח אתכם בחזרה למעבדה, שזה אזור המחיה שלי. הנושא שלנו, אולי אפשר לכבות את אורות הבמה, ואז יראו יותר טוב. עוד פעם, ניסוי אחר. כן. אולי גם חלק מהאורות למעלה אפשר לכבות? טוב, נשאיר את הניסויים האלה לניסיונים. הנושא שלנו היום הוא התגלית של הגבישים הקוואזי-מחזוריים. אני מעדיף לדבר באנגלית. יש כאן מישהו שלא מדבר עברית? תרים יד ואז ישר אני מדבר באנגלית. אוקיי. I'll speak English, if it's okay with you, okay? That's because all the slides are in English. So the subject is the discovery of quasi-periodic materials, and my name is Dan Shertman. Let me take you to the mid-80s. In the mid-80s, year after year, from 1984 to 1986, there were three very interesting discoveries on the structure of matter and its properties. The first discovery, 1984, was the discovery that my name is on, and that later on was given the Nobel. And these are the quasi-periodic crystals. A year after that, fullerenes were discovered, buckyballs, then later nanotubes and so on. And now you have a nanocenter. And a year later, high-temperature superconductivity, year after year. All these three discoveries received the Nobel. Now, let's start with the last one. High-temperature superconductivity was a very interesting discovery, and people were very happy to hear that not as before, superconductivity could be at higher temperature than expected and what the theory predicted. But there was no objection to the discovery. And because of the applications behind high-temperature superconductivity, people felt that it's a wonderful discovery. And very soon after discovery, the Nobel was bestowed on the discoverers. And then, let me take you back to fullerenes. Fullerenes is just another way in which carbon atoms can form a ball or a tube. And that was not forbidden by any law of nature. And it was received immediately as a very nice discovery. And last year in physics, Again, Nobel was given to another way in which atoms can form a single layers. Not a tube, not a ball, but just a layer. And they measured the properties, and this is why they got the Nobel. Quasi-periodic crystals, when they were discovered, received immediate resistance. And that is because the symmetries involved in quasi-periodic materials were forbidden by the laws of crystallography. And I will talk about this resistance as we go along. So, before we start, let me explain to the students among you some terms. And I will talk about order, I'll talk about periodicity, and about rotational symmetry. So let's start with order. What we have here is a drawing of a plane of, let's say, these are atoms on a plane, and clearly there is order here. They are not assembled the way they want. There is an order in this structure. So this is a plane, let's say, in a cubic structure or so. Now, about periodicity. If you look along this red line on the left, you see that there is periodicity. There is a certain distance between atoms which repeats itself. And this is true for each and every direction that you go. For instance, in this direction, and also in this direction, and so on. Any direction that connects two atoms have infinite number of atoms which are periodic in a periodic structure. Now, let's say a word about rotational symmetry. What we have here is a plane, or let's say projection of a crystal, which have a fourfold rotational symmetry. And in order to see that, I have attached the red handle on the top, and let's see what happens when we start to rotate it. So we can rotate it 90 degrees, and if not the handle, you wouldn't know that I did anything. It looks just the same. And again, and again, and again, and we are back to where we were before. So this one has a fourfold rotational symmetry. So now we know something about order, about periodicity, and about rotational symmetry, and I will use these terms as we go along. May I suggest you to turn off the lights completely? Really, we need to see better. Okay, אפשר לכבות את האורות לגמרי? Oh, all right, now we're talking. Okay, so let's define rotational symmetry. Let's define rotational symmetry. Okay, fine. An image has a rotational symmetry if there is a center point around which the object is turned a certain number of degrees, and the object still looks the same. That is, it matches itself a number of times while it is being rotated. Let me give you a few examples. For instance, the card on the left has a twofold rotational symmetry. You can turn it 180 degrees, and it will look the same. And then back. This one here has threefold rotational symmetry, fivefold, sixfold, and you can make any rotational symmetry that you want for a motif. This is a motif which has certain rotational symmetry. Now let's say a couple of words about crystallography. The science of crystallography really started 100 years ago, in 1912, by the famous experiment by von Laue and his co-workers, who performed the first X-ray diffraction experiment. And a year later, de Bragg, father and son, turned the tool of X-ray diffraction into a science of crystallography by showing that you could find a lot of information about the crystal just by using the diffraction patterns obtained by X-ray diffraction. And when this happened, something very interesting happened, and we have to learn from it. You see, crystallography was there before. The people that work in geology found many crystals with facets, and they measured the angles between the facets, and imagined that because these are the angles, then the structure of atoms should be this way or this way or this way, and created a pseudoscience of crystallography. Why pseudoscience? Because there were no experimental evidence. It was in their minds, and they were right. When X-ray crystallography started, suddenly there was a tool in the hands of the scientists, and immediately these scientists who did X-ray diffraction distinguished themselves from those primitive biologists with their facets. No, that is no science. We have the tool to do precision science, and we are X-ray crystallographers. Now, when they distinguish themselves from the other investigators and put the boundaries to their science, they also put the boundaries from above. And when the results came from electron microscopy, they said, this is not the right tool. We are X-ray crystallographers. You come and bring us information from X-rays, and then we can talk. Electron microscopy, we don't know about that stuff. That was bad. And but it stems from 100 years ago, when they distinguished themselves from below, they also bordered themselves from above. So much for crystallography. And let's see what was the crystal definition until 1991. You see, the community of crystallographers have a union. It is called the International Union of Crystallography. International Union of Crystallography. This is the international union that up until the year 90 or so, was the union of the X-ray crystallographers. And the definition of a crystal during that period was something like that. Here is from a book by Quality. This is X-ray diffraction. A crystal is a solid composed of atoms arranged in a pattern periodic in 3 dimensions. So a crystal is periodic. Okay. Another definition, this is from the book by Barrett and Masalsky, says atoms in a crystal are arranged in a pattern that repeats itself in 3 dimensions throughout the interior of the crystal. Many words, same definition. Exactly the same. So order was synonym to periodicity, and all crystals that were studied from 1912 until 1982, for 70 years, all of them were ordered, of course, this is why they are crystals, and they were also periodic. And periodicity was synonym to order. And then there was a book that we studied, and I'm sure that many physicists at least here studied this book. This is a book by Kittel, and you see the part that is marked in green. I know you cannot read it, this is why I enlarged it for you. And it says the following. We can make a crystal from molecules which individually, each molecule, can have 5-fold rotation symmetry. But we should not expect the lattice to have 5-fold rotation axis. Of course. Why not? Because in a periodic lattice, you cannot have a 5-fold rotation symmetry. So let's see some examples. This is a high-resolution electron microscopy of diamond, which I took many years ago. And each white spot is an atom. And clearly you see that there is order and there is periodicity. And in such a structure, the rotational symmetries that are allowed are 1, 2, 3, 4, and 6, no 5, and nothing beyond 6. 1, 2, 3, 4, 6, no 5, and nothing beyond 6. No 7, no 8, no nothing. And that's true from the mathematical point of view. This is true. And the diffraction pattern, this is an electron diffraction pattern. The diffraction pattern from a periodic lattice looks like this. These are not atoms. These are diffraction spots. This is the reciprocal space. We have the real space in which the atoms exist, and we have the reciprocal space in which the diffraction spots exist. But the rules, the symmetry rules, are the same. So in a diffraction pattern, also, there is, if the substance that you take diffraction from, if the crystal is periodic, so is the diffraction pattern. If the crystal is periodic, the diffraction pattern is also periodic, as you can see here. And the rotational symmetries that are allowed are 1, 2, 3, 4, 6, no 5, and nothing beyond 6. This was the wisdom. And then, in 1992, a new definition of a crystal emerged, 1992. And this is the most beautiful definition of anything in science that I've ever seen. And let me explain you why. Let's see what it says. This is the new definition of a crystal. It says, by crystal we mean any solid having an essentially discrete diffraction diagram. And by aperiodic crystal we mean any crystal in which three-dimensional lattice periodicity can be considered to be absent. So what's special about this definition? Well, first of all, it defines crystals not through the order of the atoms, but through the diffraction pattern. A crystal, by crystal we mean any solid have an essentially discrete diffraction diagram. If you see an essentially discrete diffraction diagram, then we have a crystal. But also, it doesn't say a crystal is. It says by crystal we mean. Very soft definition. It doesn't say, when you read further, it doesn't say by aperiodic crystal is. No, it says by aperiodic crystal we mean any crystal in which three-dimensional lattice periodicity can be considered to be absent. This is a soft definition in a hard science. This is a modest definition. This is an open definition. This is a humble definition. And this is why it is so beautiful. A humble scientist is a good scientist. An open-minded scientist is a good scientist. And this definition is an example of good science because it is so humble, because it is so open. Hey, what happened? What happened to crystallography that suddenly we need a new definition for crystal? And not only that, it's a very humble definition. This is in the International Union of Crystallography. I mean, the crystallography was a mature science. It was believed that nothing else will be ever discovered in crystallography. We understand everything, we X-ray crystallographers. Not so. Not so, as we can see. 1982 was the 70th birth of crystallography, and the year in which quasi-periodic crystals were discovered. Now, let's look at my logbook. This is my logbook, and the date is April 8, 1982, as you can see on the upper right side. And the material is aluminum 25 weight% manganese. This logbook of electron microscopy was meant to be read by me only. Nobody should ever look at this page or any other page in this book. These are notes that I write to myself. And as you will see, it's in shorthand. I mean, these are just signs and marks that I write to myself. But as fate decided, it became a very famous one because, as the Nobel Committee said, this is one of the single events in the history of the Nobel Prizes that a discovery can be dated to a certain date in history, April 8, 1982. This is the date. Now, let's see. The numbers are, I am talking about the right-hand side page. The number 1720, this is plate number 1720 on the transmission electron microscope. At the time, we were used to take pictures on plates. Not only that, the plates were made of glass. Glassy plates, like in the old times. SAD doesn't mean that I was very sad. It only means that it is a selected area diffraction pattern. Selected area diffraction pattern. And so on. So plate number 1724, I saw something very interesting, and I will show you the picture, and I will describe what was interesting. And then plate number 1725 says selected area diffraction pattern from the previous area, tenfold, 3 question mark, because what I saw was a tenfold diffraction pattern And the picture of that, I'm going back here. You see, look at plate number 1724. This is the plate with a magnification of 36K. That means 36,000 times the magnification of the microscope. And this is how the picture looked like. What was strange about this is that, as you will see, for instance, here, there are several crystals, grains, here and here and here, that are pitch black, very black. This can mean one of two things. Number one, it can mean that the area there is very thick so that the electrons cannot go through. This is obviously not pertinent here because the other area nearby is very thin. Or it can mean that that crystal diffracts heavily. So most of the intensity goes for diffraction. And I said, whoa, that's quite interesting. Let's see what the diffraction pattern looks like. And it looked like that. So I took the diffraction pattern. This is the next plate. And it looked like that. And what we see here is a diffraction pattern, which is different than any other diffraction pattern that you saw until now. You saw only one. That was periodic and ordered. Here, there are two things which are different. Number one, if you count the number of spots, as I have done at the microscope, around one of the circles, then you will see that there are 10 spots. And if I had a good laser beam, which I don't, then I could even count it with you. But so I counted one way. I said, 10? No, cannot be. And I count the other way, tenfold, and this is what I wrote in my logbook. Another thing that was very strange, tenfold is forbidden, remember? The other thing that is missing here is the periodicity. If you take a row of points, any row of points, let's start in the center and go in this direction, okay? You see that there is no periodicity. The distances between the spots are not periodic. Obviously, something new and possibly exciting. However, based on my previous knowledge, I thought that what we have here is a series of defects in a crystal called twins. Twins are like grain boundaries, but in a very special angle between them. So if these are, in my fingers, designate atomic planes, then we have another one which is mirror image with this atomic plane. And this is a twin of that. And in between them, we have a twin boundary. If you have 5 of them together, and you take a diffraction from all of them, or 10 of them together, then you will get a diffraction pattern, which is a composite diffraction pattern, not from a single crystal, but each spot comes from a different one, and they can do that. It can look like that. How did I know that? Because I have seen it before. And I will show you an example. So what they did on the first day of the discovery was to find the twins, just to perform certain experiments called dark field experiments to find the twins. Couldn't find the twins. And then what they did was to perform a convergent beam electron diffraction. Convergent beam electron diffraction means that you converge your beam onto a point, very small point, as small as you can, and take a diffraction from that area. And if that area will hit just one periodic crystal, then you'll see one periodic diffraction pattern. And you move to the next one, you see another one rotated. That didn't happen. There were no twins there. And I knew in day one that there were no twins there. Why do I mention that? Because my main opponent didn't believe in my results and claimed that there are twins in these crystals, and he did that quite a few years, 16 years after the discovery. Okay, so let's go further. The 5-fold or 10-fold rotational symmetry, by the way, as you have seen, there was a 10-fold rotational symmetry. It turns out, and I could not know from that experiment that it's not really 5-fold, 10-fold, but rather 5-fold. It required a different experiment, which I did a few days later, and to see that it's really 5-fold rotational symmetry, but it doesn't matter now. So if you take the crystal, this is the 5-fold, and then there is 2-fold and 5-fold again, and so on and so forth, 3-fold, 2-fold. What I do here is very simple. Let's say that this is the crystal that I take the diffraction from, and I hit it with an electron beam and receive diffraction underneath. And then I tilt and turn the crystal in each and every direction, And in each and every direction, I would get a different diffraction pattern. This direction, this direction, this direction, and so on. So this is the assembly of diffraction patterns which define more or less the whole crystal. Now, when I was a student at the Technion, somebody mentioned here that I didn't study in this university. And let me tell you something. I tried. And this is true. I went to study biology here, and I was not accepted. And fact of life. And the Technion said, well, we get all those morons, let's get another one. So I studied at the Technion. So anyway, in one of my classes, I studied, it was X-ray crystallography class, and one of the questions that was asked was, in the exam, prove that five-fold rotational symmetry in a crystal cannot exist. Prove that five-fold rotational symmetry in a crystal cannot exist. And I proved it, and I passed the test. And here I am. Had I not, I wouldn't be here. So let me show you one such proof, which is quite nice. In order to prove that five-fold rotational symmetry does not exist in crystals, let me rephrase it. Now we should say five-fold rotational symmetry does not exist in periodic crystals, right? It exists in quasi-periodic crystals, but not in periodic. How did I prove it? Very simple. Take two atoms, P and Q, mark here, P and Q, but choose the atoms in the lattice which are the closest together, the ones that are closest together, shortest distance between them. And the distance is R, as you can see here. And then, if five-fold rotation symmetry is allowed, then we should be able to rotate Q around P 5 times, P around Q 5 times, and let's see what happens when we do that, okay? So let's start to rotate Q around 5, 1, 2, 3, 4, 5, and then we have Q prime. There should be an atom where Q prime is. And let's do the same thing for P, 1, 2, 3, 4, 5, and we have P prime. And there should be an atom at P prime. But the distance P prime, Q prime is shorter, just because of geometrical reasons, than the distance R. But we said that it shows the smallest distance. So that cannot be, and this was a proof that was accepted by my professor, and everybody was happy. So why did I think that there were twins there? Well, let me show you. This is a picture from the electron microscope that they took many years before the discovery of quasi-crystals, sometime in the 70s. And it was so trivial that I never published this work, because I thought that, I mean, nothing to it. Turns out that colleagues from mine in China, years later, published about 5 papers on these results. Okay. So here we have a crystal which is twinned. You see, this crystal is composed of 10 crystals. Each one of them is like a petal of a flower. There are 10 of them there. And in between each 2 of them, we have a twin boundary. So what we have here, this is a single crystal. This is a single crystal. They are twin related. And in between them, there is a twin boundary. Now, if you take a diffraction pattern from one of these, you get a periodic diffraction pattern, like from every periodic crystal. But if you take a diffraction pattern from all of them together, you get a superimposed, 10 diffraction patterns superimposed on each other, and then it looks like that. This is the exact diffraction pattern that I took. And this is what I had in mind when I discovered quasi-periodic materials, that these are twins. I was looking for the twins. Here it's very clear, couldn't find any twins. If you want to see just one crystal, then one crystal is like that. Okay? And you have 10 of them superimposed on each other. This is pseudo 5-fold rotation symmetry. And here you have the same phenomenon in diamond. These are twins in diamond that I took years later. So it's quite abundant. You find them in nature. But these are twins, not the discovery. And then in order to find these twins, I performed a series of dark field experiments. This is in day 1, April 8, 1982. These are the experiments that I performed. And what I did here was, these are called dark field experiments. Let me explain to you. I wanted to like electron microscopy. Maybe then you can go to Dr. Ina Popov and ask her to teach you more about electron microscopy. So let me give you a little introduction about contrast analysis in electron microscope. As the electron microscope works, there is an electron beam that goes through a specimen. Here is your specimen, which is very thin, so thin as to allow electron beam to go through. Let's say 100 nanometers thin. And the electron beam goes through. When it goes through, at certain angles, it will diffract. So beams will come in each and every direction, and also there will be a transmitted beam and diffracted beams in different directions, okay? Underneath, there's an aperture. Aperture is a piece of metal with a hole in the center. High-tech, piece of metal with a hole in the center. And that aperture allows one beam to go through. So what you can do, let's say that these are the beams in one direction. We have these and so on. Let's say that this is the transmitted beam. If you allow this beam to go through, then you get a bright field image formed. But if you tilt the beam so as to allow this beam to go through, then you get a dark field image. So you can have one bright field image and many dark field images. Okay? Hey. So these are dark field experiments using different beams, and on the left-hand side, you see the diffraction pattern, and the beams that were used for dark field experiments are marked. And I was hoping to see those twins, but I could not see any twins in any of these dark field images. Okay, the last experiments that I did that day was micro diffraction pattern or convergent beam diffraction pattern, or convergent beam electron diffraction, seabed it's called nowadays, and it contains a lot of information, a wonderful tool. But here I just use it to get a diffraction pattern, and what you do here is that when you converge your beam onto a small spot, then you can try and find a single twin, couldn't find any. Wherever I moved, the diffraction pattern appeared. And then the last experiment was very, very educating. I did not do that experiment. I did not have, at the time, a high-resolution electron microscope, and my electron microscope did not allow to do that. But friends of mine in France did that experiment, and they sent me the results. And the results are very beautiful. You see, this is the lattice image. Lattice image meaning that you see the atoms in what was called later on the icosahedral phase because of the icosahedral symmetry. We will talk about that. So here is the diffraction pattern, and here is the image. And the image is a Fourier transform of the diffraction pattern, and vice versa. Now, what my friends did, they also took an optical diffraction pattern. An optical diffraction pattern is a pattern. You take the picture of the lattice image, you put it on a slide. Nowadays, you can do it on the computer within 2 seconds. But at that time, we put it on a slide, make it very, very small, and shine a laser beam through the slide. And what you'll get an optical diffraction. And that optical diffraction looks like the one on the right. So this is an electron diffraction, this is optical diffraction. So you can say, okay, big deal. Both are Fourier transforms of the image, 2 different ways. That is true. But let me show you what experiment you can do. Nowadays, you can do this by computer. You can take and select a small area, and then make it smaller and smaller, and shine the laser beam only in that area. And when that area becomes smaller and smaller, this diffraction pattern doesn't change. It will disappear for lack of information, but it doesn't change. That means that, hey, this 5-fold rotational symmetry is really a property of the material itself, and not a combination of anything else, periodic. And this is a modern picture of quasi-periodic material, and you can see all these motifs arranged in a quasi-periodic way. I will talk shortly about quasi-periodicity. You will all understand it very well. This was the first paper that I wrote with my colleague Ilan Blech, Professor Ilan Blech from the Technion, who helped in offering a model that explained my findings. That paper was sent to Journal of Applied Physics. It was rejected within a couple of weeks. And they said, send it to a metallurgical paper. It will not interest the community of physicists. So I sent it to a metallurgical journal. And it was accepted and published. But it was published months later. And this is not the paper that made the breakthrough. The paper that made the breakthrough is this. And then there were two more people joining. Denis Gratias, a mathematical crystallographer from France, and John Kahn, an eminent thermodynamic person from the United States. We wrote a shorter paper, more condensed, that did not contain the Ilan-Blech model, and we sent it to PRL, Physical Review Letters, and it was published very quickly. And when the paper was published, hell broke loose. Because a community of avant-garde young scientists from around the world, mainly from France, but also from other countries, China, Japan, Germany, oh, you name it, United States, all joined force. And immediately a community was formed of people who not only believed in quasi-periodic materials, but also investigated them thoroughly, theoreticians, experimentalists, and we were the avant-garde. I was not alone anymore. We were the avant-garde who deciphered the code of these new materials. The year was 1984, the end of 1984. Now, let's talk a little bit about icosahedral symmetry, because these structures that I discovered have icosahedral symmetries. Later on, other quasi-periodic materials were discovered by colleagues of mine that had different structure. But this was the icosahedral symmetry. What you see here is an icosahedron, which is one of the plateau solids. And if you look from this point to the center of the icosahedron, you see there is 5-fold rotational symmetry. If you look from the center to the center of the crystal, of the icosahedron, you see there is 3-fold rotational symmetry. And if you look from one of the bars into the center, you see that there is 2-fold rotational symmetry. So this is the icosahedral symmetry. This is the icosahedron. And this is why we call the phase the icosahedral phase. And here is a better example, Beitar Yerushalayim. Okay, I'm sure that some of you like Beitar Yerushalayim. So football will talk to you maybe better than drawings of those engineers. And so we have in the football, soccer ball in the United States, a 5-fold rotational symmetry at the upper one. The lower right, we have 2-fold rotational symmetry, and then we have 3-fold rotational symmetry. A football has an icosahedral symmetry. I'm sure you all knew about it. Okay, and now let me tell you about the years of rejection. And the rejection to the discovery came basically in 3 stages. Stage 1, I was alone. I was alone in a large lab of eminent scientists, and here I am coming out from the electron microscope with all these prints. I printed those slides, showing my colleagues and saying, hey guys, see what I got. And I have a material with 5-fold rotational symmetry. And other symmetries, but at least in certain direction, it has 5-fold rotational symmetry. And he said, Danny, you know this is impossible, right? We know that you are from a Technion. I don't know what they teach you there, but let me tell you, this is impossible. So much so that my group leader came to my office one day after a few months of a little turmoil, smiling sheepishly and putting a book on my desk and saying, Danny, please read this book and you'll know that what you're talking cannot be. And I said, well, you know, I'm a lecturer at the Technion and I teach these subjects and I know this book, and I'm telling you my new alloy is not in the book. So he was not very happy with my answer, took the book, came back sometime later and said, Danny, you're a disgrace to my group and I would like you to leave my group. Just, I don't want to be associated with you. And so I left his group. It's not a big deal to leave the group because all it meant was to report to a different secretary. I didn't have to move from my office. I didn't have to move from my laboratory. But it was this type of rejection. Now, this was the extreme. The median people told me, at least one of them, said, Danny, this material is telling us something, and I challenge you to find out what it is. So this was an encouraging reaction to my findings. So this was during 1982, 1984, and I didn't feel very good at that time because, and if you want to know how I felt, that's about something like that. Everybody was sort of, I mean, I had to walk tall, and I was not. So this was during that year. After the publication, 1984, 1987, I was not alone anymore. We were a growing group of excellent scientists around the world who were with me, and I led a very powerful team that grew almost daily, and a community was formed. However, up until 1987, the official community of crystallographers did not accept quasi-periodicity. They said, electron microscopy results are not acceptable to us. We are X-ray crystallographers. This is the science of X-ray crystallography. You bring us X-ray results. And for 3 years, we could not have X-ray diffraction results. And the reason was that in order to perform an X-ray diffraction experiment, you need a crystal of some size, maybe like a grain of sand, but something that you can hold in your hand, put it on the tip of a pin, and shine an X-ray beam through it. And we did not have that. We did not have large enough crystals. Until 1987. In 1987, friends of mine in Japan and in France grew large enough crystals, took X-ray diffractions, and sent it to me to be presented in the meeting of the International Union of Crystallographers in Perth, Australia. Perth is on the west coast of Australia. And then I presented these results. I'll show you immediately these results. And then the community said, okay, Danny, now you're talking. Now let's have a serious look at what you have here. And these are the guys that later on, these are the X-ray diffraction patterns, beautiful diffraction patterns. You can see clearly the 5-fold, 3-fold, 2-fold, very nice. And these are the pictures that brought the new definition of a crystal and a new definition of non-periodic crystal. From 1987 till 1994, the resistance did not die. And the leader of the resistance was Professor Linus Pauling, possibly, arguably, the best, the most famous chemist in the 20th century. He wrote the books. He taught us what chemistry is fundamentally. And he said the following on stages. Danny Schertman is talking nonsense. There are no quasi-crystals, only quasi-scientists. And he was Linus Pauling, whom I think really he was a great scientist. He was a flamboyant speaker. He stood on stages, waving hands like a politician. And the crowd behaved like in a political meeting. They said, whoa. And I was there. So Professor Linus Pauling, he continued until his last day to be a non-believer. He died in 1994, and with him, the resistance to quasi-periodicity died, and from that day on, there was no resistance. Why was Linus Pauling so effective? Because he was not alone. He was the idol and the father of the American Chemical Society. American Chemical Society is a huge society, and he was the prophet. And what he said was right. And what Danny Schertman said, where is he, was wrong. So let me tell you one reflection. In the forefront of science, there is not much difference between science and religion. You'll be surprised. People have their beliefs. I have my prophet. Your prophet is no good. Mine is better than your prophet. Huh? like religion. Then when things enter into the books, everybody accepts everything. But before that, at the forefront, when there are these horrible arguments, bitter arguments, people argue. Now, I will summarize this later on for you. So this was Linus Pauling. Who else had seminal contributions? Roger Penrose, British mathematician. Alan Mackay, British mathematician, live in our time. Roger Penrose discovered the Penrose tiles, which can tile a two-dimensional space, a floor with tiles which have five-fold symmetry and no periodicity. Alan Mackay took his tiles, took Penrose tile, and performed the diffraction experiment and shows that Penrose tile will diffract with five-fold rotational symmetry. Ilan Blech, another great contributor to my research, gave the first model of quasi-periodicity, quasi-periodic materials. And Dov Levine and Paul Steinhardt gave the mathematical explanation to quasi-periodicity. Dov Levine is a professor at Technion now. He was a student at the time. And Paul Steinhardt was his professor. And it was in Pennsylvania at the time. And they took, Paul Steinhardt and Dov Levine, took Penrose tiles and Mackay's work, my diffraction pattern, put them together. Lo and behold, it's the same thing. So they said, OK, Danny's findings are really tiles, three-dimensional tiles, and they built their model. Each one of them had a great contribution. Now, let me take you a little bit off science and show you what was the feeling during that period of time. 1986, in the month, down here is the month, oops, sorry. Down here is the month, 1986, January, February, March, April, and so on. And here is the number of publication. N is the pages in the bibliography, and the number here is 1 over n. So each page in the bibliography contains maybe 20 papers, 25 papers, each page. And this number is 1 over n. As you go down, so grows the number of publications. And this was drawn on a piece of paper by a friend of mine. He brought it to lunch, and I confiscated it from him because I thought it will be a lesson to history, and it is. So what you see here, he counted the number of pages in the bibliography in February, and then in March and April, and so on, and he drew a straight line. It's to his horror and to our horror. By December of 1986, the number of publications should have reached infinity. Here is the scientific proof. And all the forests of the Amazon will have to be cut just to make the paper to print all these publications. Well, it didn't happen, but the feeling was that of an explosion, and that's the way it was. Okay, now I don't have enough time to go through. Well, let me just go through this, and then we will skip the fundamentals of quasi-periodicity. Let me show you a mathematical technique that you can use at home to take a periodic array, make a cut and projection, and get a quasi-periodic array. Take periodic array, make cut and project, and receive quasi-periodic array. Let me show you how it's done. So what we have here is a two-dimensional periodic system, and this is, let's say that in each intersection of two lines, there is a mathematical point there. No, not without dimension, just point. And now we can make a cut. We make a strip. We create a strip in that two-dimensional periodic array. And that strip is not going in any direction, just in any direction. It goes in an irrational direction, which is called also the Fibonacci number, tau. So tangent of alpha is 1 plus root 5 divided by 2, and this is 1.618 and an infinite number of digits behind it. When I say that I choose this direction to be irrational, it means that if I start at a lattice point here or at a mathematical point here, this line will never touch any other point. Why so? Because if it will touch another point, then the tangent will be a rational ratio. And therefore, it cannot touch any other point. Okay, so now that we have done that, we can make the projection. We choose all the points that are within the strip and project them onto the line on the right. So, as you can see, each point is selected and projected. And now we can look at the distances between these points. The distance from here to here, from here to here, and so on. So this is large, large, small, large, large, small, large, small, large, large, small, and so on and so forth. This is a quasi-periodic array. There is no motif that repeats itself in this, along this line of any size. No motif of any size which repeats itself. This is a quasi-periodic array or quasi-periodic array in one dimension. So we took a higher dimension, two-dimensional space, cut and project, and we received a quasi-periodic array on a lower dimensional space. Now at home, you can take a six-dimensional space, cut and project onto a three-dimensional space, and you receive a quasi-periodic crystal. So I have chosen one in which the periodicity comes every 11. Here, you count. You see there is one point up there. Go up from here, you see that there is one point in which the red line meets exactly that point. And so this is a periodic tangent because you can count this divided by this, 11 divided by 7. This is 1.5714, close to 1.618 and so on, but it is periodic instead of quasi-periodic. And the periodicity is large. Okay? The periodicity is quite, the motif is large, like that, like that, like that, but that's okay, but it is periodic. If you have a periodic array which is close, very close to quasi-periodic array, we call them approximants. And so it is in crystals. Crystals that are periodic but have a large unit cell, and they are similar, close, very close to being quasi-periodic, we call them approximants. So this is interesting that now periodic crystals attach themselves to quasi-periodicity and say, we are special. We are an approximant of quasi-periodic materials. Hey. Okay, so these are the approximants. And I mention it because you may find it in the literature. Now, I don't think we have enough time to talk about Leonardo da Fibonacci da Pisa, but let me just go through very quickly. This is Mr. Leonardo. This is his statue. He was buried behind the inclined tower of Pisa, under a roof. There is a graveyard there. If you ever visit the inclined tower of Pisa, I suggest that you go just behind it and find his grave. He was the greatest mathematician of his time. And in the year 1202, he published this series of the rabbit experiments. I will not go through that. I want to go to the end. Just show you Penrose tiles. These are the Penrose tiles that I discussed before. And this is three-dimensional quasi-periodic crystal. The photograph was taken in my laboratory, I think, by Ina in the old days when she was there. So, and this is in the system magnesium zinc serum. Beautiful crystal. Now, I was asked to talk about Japanese aesthetics, and so I will mention it in 1 minute. What you see here are quasi-crystals, and it was taken by a friend of mine from Japan named Ampeng Tsai. He is a professor at Tohoku University, and he used artificial coloring of a picture from a scanning electron microscope to show that these look like the flowers of the cherry tree in the season. So these are quasi-crystals that reminded him of cherry blossom. So here's the connection. Let's sum up. While before, order was synonym to periodicity. Nowadays, we know that order can be periodic and can be quasi-periodic, and it's open. We are willing to accept any other discovery in this area. Now, in order to sum it up, and before you ask a question, I will ask a question and answer you my answer. Okay? Why is it that quasi-crystals were never discovered before 1982? After all, for 70 years, hundreds of thousands of crystals were studied. So why is it that nobody saw anything that has to do with quasi-periodicity? Maybe because quasi-periodic materials are very rare. And so I happen to stumble upon one of them. Or they are not very stable. You look at them, they transform. Or you touch them, they transform. Or maybe they are difficult to make. And I, with my skills, managed to make one. And so on. So what is it? Well, are they rare? Answer, no. Quasi-crystals are not rare. There are hundreds of them. The list here shows you part of the quasi-crystals based on aluminum. And there are many based on other metallic elements. So there are many hundreds of them. They're not rare. This is not why nobody saw them before. Maybe they're not stable. Well, many are not stable, but some are stable. And the ones that are not stable, you have to heat up to 300 or 400 degrees C in order to transform them. Below that, they're stable. So for any practical purpose, they are stable materials. That's not the answer. Maybe they're difficult to make. Not at all. Anyway, you make any metallic alloy, you can make quasi-periodic material. You can cast them. You can rapidly solidify them. You can do single crystal growth. Electrodeposition, you can do CVD, you can do PVD. Anyway, you produce any material, you can produce easily quasi-periodic materials. Maybe they are made of very expensive materials, very pure praseodymium with very pure yttrium. No. We talk aluminum, iron, copper, cheap materials. Anybody can buy them and make them. No, these are not the answers. So why is it that quasi-periodic materials were never discovered before 1982? Let me give you my answer. Answer number one, TM, transmission electron microscopy. Quasi-periodic materials could not have been discovered but by an electron microscope. Why so? Because the crystals were very, very small. My crystals were 2 microns in size, and so were all the crystals. Even though people tried to grow large crystals, it took 3 years for somebody to grow large enough crystal, which was like a grain of sand, in order to take the first active diffraction. So TM should have been the tool. That limits the number of researchers that could find quasi-periodic materials. Number two, professionalism. You have to be a professional. This is my message to the young people here. If you want to achieve anything in your life, be a professional in something. Something that you like, something that you think will take you into the future. But be a professional. Study everything to know and become a professional. What does it mean, a professional on the transmission electron microscope? Ina here is a professional. I am. A professional is somebody that not only has a driver's license on the electron microscope, driver's license on the electron microscope. When you get the permission to work at the microscope, it has only one meaning. It means that the man in charge or the woman in charge trusts you that you will not destroy the machine, that hammers, you leave at home the hammer and the screwdrivers. Okay, we trust you, you will not destroy the machine. That doesn't mean that you know what to do with the machine. In order to know what to do with the machine, you have to work hard for a long time. It doesn't come instantly. You have to dedicate a lot of time to electron microscopy. Sometimes it takes years. And then you become a professional. It depends not only on the students, it depends mainly on the professor, because it is expensive. If you want to allow your students to do TM as much as he wants or she wants in the laboratory, then it will cost you some 100 shekels per hour or so. And some professors said, no, just you work for 5 or 10 hours, come with results, and that will be it. The rest you will do in our laboratory. If you want to educate electron microscopists, you have to let them work as much as they can, as much as they want. Hundreds upon hundreds of hours. And yes, it is expensive. But for my laboratory, we have at least 2, 3 experts. Each one has a good position in different university doing electron microscopy. Okay, so this is about professionalism. You have to be a professional. And then you have to have a tenacity. What does it mean? Well, it means that you have to have persistence. You have to have persistence. You have to be, when you are a professional working on a TM, and you trust yourself, and I was the worst critic of my results, then you can stand tall and say, I know I am correct. I'm listening to you, but don't come to me with theories. Come to me with experimental results that contradict my results. If you don't come with experimental results, and you just came with Gedanken experiments, then that's not good enough. Then you are not right. And Linus Pauling is a good example because he was wrong all the way. So, but you have to have a tenacity. You have to believe in yourself. Now, believing in yourself has to do with professionalism. It also has to do with self-confidence. If your mother loved you when you were very young, you grow up with self-confidence. And then you can stand tall against the community. And the last one is courage. Well, courage is very individual. In my case, I was a senior lecturer, Marze Bachir at the Technion, and I had a few of our faculty who did not like me, and they did anything to impede my promotions. And this was a case in which the greatest scientist of the century, Professor Linus Pauling, says that Danny Schachtman is talking nonsense. Are you going to give this person an associate professor when the greatest man says that he's talking nonsense? So you have to have some courage and do that. This is my answer to why quasi-periodic materials were not discovered before me. Let me give one example, which is real. There is one person at least who saw the 5-fold diffraction pattern before me. He did his PhD in Belgium. Van Tendeloo was his professor. Maybe some of you know this professor. And Van Tendeloo, years after the student graduated, he was a PhD for many years, went through the slides in the laboratory and found something that looks exactly like mine. He called the student and said, hey, you know that you saw what Danny Schachtman saw years after you? He said, yes. Why did you tell me? Says the student, if I told you, you would want me to stay 2 more years to understand the problem? I wanted to become a PhD. Thank you very much. Okay? So you have to have the tenacity. Don't let go. Don't let go. Okay. Thank you very much.
תודה, דני. יש מקום לשאלות, אם אתם רוצים לשאול. כן, אודי.
I'm curious to know about the relation with the mathematical work of Penrose. Penrose, if I remember correctly, published his first paper in 75 or so.
Right.
So mathematicians had the idea that all they can come through the... Oh, sorry.
So my question is about the relation with
Penrose work on aperiodic tiling. So I'm curious to know why you think it took so long for a mathematical idea that was present already in 1975, but the possibility to have order through aperiodic structure to penetrate and link to your discovery. Why did it take so long, and why wasn't this link made before?
Okay, the answer is the following. Penrose style, the link was not Penrose style. The link was the work by Alan Mackay, who showed that you can create diffraction pattern from Penrose styles, which has a 5-fold rotational symmetry. That was published in 1981, just a year before my discovery. And I was not exposed to that paper. As simple as that. It was not in my field, in mathematics. Penrose styles became very famous because Gardner published them in Scientific American as mathematical games. And then everybody knew about Penrose tiles. But Mackay experiment was just a scientific experiment, and it was published in a mathematical journal, and I was not exposed to it. So if I were exposed to it, I would solve it immediately, but it took some time.
Okay. Thank you very much.